Hi everyone, my name is Fernando Pereira, and today I will talk about our experience at UFMG's Compilers Lab, designing and implementing optimizations for tensor compilers. But before I start, let me introduce you to UFMG and to Belo Horizonte. For those that don't know, UFMG is located in the city of Belo Horizonte, which is the capital of the state of Minas Gerais in Brazil. Belo Horizonte is a large city, the sixth largest in Brazil, with a population of almost 2.5 million. If we count the metropolitan area, we might have perhaps 6 million people living around there. And Belo Horizonte fosters a nice software development environment. The city hosts Google's largest development office south of the equator, for example. And there are other big tech companies there as well, for instance, Accenture and also Cadence Design Systems. That's Cadence's largest development office south of the equator, just like Google's. And much of this is due to UFMG. UFMG is the largest university in Belo Horizonte. Well, that's one of the largest public universities in Brazil, with almost 45,000 students, out of which 15,000, more or less, are graduate students. It's considered a good university in Brazil, and competition to get in computer science is very tough. Last year, the applicant to seat ratio for computer science at UFMG was 33.4 applicants per spot. And within UFMG, we have the Compilers Lab, where we do research on all aspects of compiler construction and design. And the lab hosts master and PhD students from UFMG's graduate program in computer science. Many of these students have contributions that ended up becoming part of popular compilers, such as SpiderMonkey in Mozilla Firefox, LVM, or Amasa 3D. As an example of such contributions, the implementation of Masa 3D's divergence analysis is based on a technique that was invented in UFMG's Compilers Lab. This divergence analysis, which Masa 3D uses, was designed more than 10 years ago by two grad students, Bruno Coutinho and Diogo Sampaio, when the lab was on its very beginning. At the time, we didn't even have a proper room. Well, much has improved since then. But today, again, I will talk about a special kind of compiler, which more recently and the compiler community as a whole, started to call tensor compilers. There are many examples of tensor compilers like XLA, TVM, ERE, MindSpore, and many more. These compilers, they read machine learning models written in some high-level language or framework like TensorFlow, Onyx, or PyTorch, and then they produce very efficient code to run these models in different kinds of hardware like classic CPUs or GPUs or TPUs or NPUs and such. What distinguishes them is that they compile programs that manipulate tensors. And what's a tensor? Well, that's data. Tensors are arrays of any dimension. So a tensor of dimension 0 is just a scalar, like an integer or a floating point number, for instance. Then a tensor of dimension 1 is a linear array, like the vectors that we have in most programming languages. And a tensor of dimension 2 is what normally we call matrices or tables. These are two-dimensional vectors. But up to this point, there's not much novelty. Scalars, vectors, and matrices are common in most programming languages, and there are specialized programming languages, mostly descendants of APL, that provide abstractions specifically for this kind of data. These are what we call array programming languages. But tensors can be arrays of any dimension. We can have 3D tensors or tensors of 4, 5, 6, any number of dimensions. Images, for instance, can be thought as 3D tensors. They consist of three main numbers stacked together, height, width, and color channels. And a tensor compiler can apply specialized operations on this, tensor data. There are many kinds of tensor operations. Maybe the most famous is matrix multiplication, but there are many more like ReLU, activation, reshaping, transposition, and such. A tensor compiler like XLA, for instance, will organize these operations in what we call a computational graph. And it's onto this computational graph that the compiler operates. Nodes are operations like matrix multiplication or addition. The edges are the data tensors, multidimensional arrays, flowing between them, between the operations. The, the use of the computational graph as the core data structure, that's what tensor compilers do. So they optimize programs by analyzing and transforming those computational graphs. So, whereas a classic compiler uses the control flow graph to analyze and optimize, traditional programs, the tensor compiler uses the computational graph. Of course, tensors and class compilers differ on their inputs. Tensor programs are usually very specialized. We can think of PyTorch, for instance, as a domain-specific language to operate on multidimensional arrays using the operations that normally we find in machine learning models. And when I talk about a classic compiler, I mean a compiler that translates a language like C to some hardware. If we use LLVM as an example of a classic compilation infrastructure, then the intermediate representation is a form of three-address code in a format that we normally call static single assignment form. Tensor compilers, in contrast, use specialized intermediate representations, like dialects of the multi-level intermediate representation. That's what we call MLIR. Here's an example of a program in the stable HLO dialect. It does look a bit like the LLVM classic intermediate representation because they more or less have the same lineage. MLIR is something that actually stemmed from LLVM. But in particular, in this example, the types and operations, they are very different. These operations form what we call the computational graph. It's a bit like if we had very complex instructions in our instruction set architecture. For instance, we have instructions to multiply whole matrices or to add them up or to extract the maximum value in a multidimensional array. These operations, once converted into machine code, will be represented by a combination of many machine instructions. And the types of the tensor are, of course, tensors, which are multidimensional arrays. In the example, we are operating on matrices and vectors of 32-bit floating point types. But that does not mean that a tensor compiler does not use a classic compiler under the hood. They usually work together. For instance, XLA needs LLVM to eventually convert its computational graph, written in something like HLO, into lower level code, like for instance the PDX that runs on NVIDIA GPUs. But the beauty of this combination of tensor and classic compilers is that the tensor compiler can act like a high-level optimizer. By high-level optimizer, I mean to say that the tensor compiler can rely on the semantics of named operations such as matrix multiplication or ReLU to carry out very effective optimizations like fusion, auto-tuning, sparsity, and such. These optimizations would be much harder to design and implement on the low-level control flow graph because this high-level semantics, I mean the knowledge that a nest of loops is matrix multiplication, it's lost in the low-level code. Incidentally, we at UFMG's Compilers Lab have worked on each one of these different optimizations, producing contributions that now are available in different tensor compilers. I shall be talking about these optimizations in the rest of this lecture. However, before we move on, let me ask you, are there questions? If you do have them, please feel free to send me an email.